Hello and welcome back to Mysteries in the Science Lab. We're here to try to learn more about the crazy realities of science.
Lately, some of our top scientists have been wondering what energy is.
So today on Mysteries in the Science Lab, we're going to figure out exactly what energy is.
To start, figure out what energy is, we have to put into two huge groups, potential and kinetic. So potential energy is how much stored up energy a non-moving object has. Potential energy is measured by using the mass of an object, how highly elevated it is. For example, like a 10-pound soccer ball is raised 10 feet in the air. It has 100 joules of potential energy.
Now, the other large group of energy is called kinetic energy, and is how much energy an object that is in motion has. So if we have that same 10-pound soccer ball that is still raised 10 feet in the air and we drop it, it has 100 joules of kinetic energy.
And right now, you may be asking yourself how a soccer ball switches from potential to kinetic energy. Well, the law of conservation of energy, it states that energy cannot be created nor destroyed. It only changes form, so at the top, a soccer ball has 100 joules of potential energy and 0 joules of kinetic energy. About halfway down, it has 50 joules of potential energy and 50 joules of kinetic energy. And right before it touches the ground, it has 0 joules of potential energy and 100 joules of kinetic energy. And the reason why I say before, right before it hits the ground, all the energy is transferred to the ground, and whenever an earthquake occurs, all of the energy is released. Watch the following videos and tell me which are example of potential and kinetic energy.
Let's go. Yep. Did you actually do it? No, I didn't know. Let's do that. Tell me that. Oh no, I'm gonna stop.
Emily, can you tell me what number 1 was?
Number 1 is an example of kinetic energy because the person is in motion.
Can you tell me what number 2 is?
Number 2 is an example of potential energy because a dog is elevated at a certain height and is not moving.
And Kira, can you tell me what the last 2 are?
Number 3 is an example of kinetic energy because while the watermelon is in motion while falling, and number 4 is an example of potential energy because the object is not moving.
Okay, let's go. Okay, look. Look at this, okay?
Yeah. It's me, and I was wondering if after all these years you'd like me to go over everything.
What are you guys
They would
doing?
say that
Actually, I know what you're doing. Gosh, over here to put this. I got this. So for mechanical energy, Kirsten's moving her fingers on the keyboard. And for radiant energy, it's the lamp. So then for sound energy, it's Emily's clarinet and the piano sound. So for chemical energy, it's the Starbucks on the table. And then for heat energy, it's coming out of Emily's clarinet barrel. For electrical, it's the TV. For the sun, it's the nuclear one. The sun.
We definitely
Yeah, we
planned
planned
that.
this. We planned all this.
You great job. That was good. We totally planned all this. Thank you.
Okay.
That's awesome.
So a good way to know all the 7 forms of energy is by using Mrs. Chin. So the M in Mrs. Chin stands for mechanical. Mechanical energy is a type of movement, so like Kirsten and Emily's fingers moving on the piano, or some of these other examples. And next, the R in Mrs. Chin stands for radiant energy. Radiant energy is any source of light like the sun. The next form of energy is S, which is sound energy. Sound energy is any type of noise. The C stands for chemical energy.
Yes.
Okay, so me and Emily are doing a experiment for chemical energy, and so far Emily has put 3 tablespoons of water and mixed it with 2 tablespoons of powdered yeast. Now I'm gonna pour half of 3% hydrogen peroxide. 12% is better, but we're using 3% in here. So we're gonna pour it in the graduated cylinder. We already tried this one. Now I'm gonna mix regular dishwashing soap with this. Doesn't matter how much you use, just not too much. Not too little. Not good. Now I'm just mix this, and we'll start. Now Emily, I'll give you the honors. I'm gonna put it, and I want to hold it until it starts doing. Now Emily's gonna pour the mixture we made in here into the mixture we made in here, and see what happens. Cool. And now it's exploding. Come look. So now we have this wonderful. And it turns warm, by the way. It's like, here, feel it. It's warm. Well, okay, well, it's warm, and it's just a foamy texture. So that's our example of chemical energy.
The H stands for heat energy, which is any substance that gives off energy like the heat coming out of the bell of Emily's clarinet. Now the E in Mrs. Chin stands for electrical energy. It's any substance or object that uses electricity like the TV. And the final letter is N. This stands for nuclear energy, which is anything that uses nuclear power like the sun.
But our next piece of the puzzle is figuring out what energy transformations are. An energy transformation is one form of energy changing into another form.
So kind of like a fan. Wait. So kind of like when they turn on a fan.
Exactly, because the electricity that powers the fan makes mechanical energy because the fan's moving. Or even when you're making toast, it's transformation because it turns electrical energy to thermal energy.
Non-renewable resources are resources such as coal, natural gas, and oil. These are called fossil fuels.
They are also called fossil fuels because you have to dig deep below on Earth to find them. And the reason why they're called non-renewable resources is because they can't be produced as fast as they're being used. But luckily, there are things called renewable resources. They have infinity amount. Oh, I heard about in the news about how they're getting energy from the waves.
So would gas for cars and coal for a train be counted as non-renewable resources? Because they aren't being produced as fast as they are being produced.
Yes, that's correct. But a windmill and a tiny solar-powered dancing people are renewable resources because you can never run out of solar rays or wind. And the final piece of our puzzle is how heat transfers. It transfers from hot to cold. Oh, I get it. So like when you jump into a pool and all of your body heat is transferred to the cold water. Exactly. Or even when you're cooking an egg, heat from the stove goes to the pan, which then goes to the egg, which cooks it. for our project, so can I help you to represent you?
Sure. Y'all look harmless. I hope so, because I'm looking at open.
Thank you.
Thanks for tuning in and watching Mr. Easton Science Lab.